Hi everyone, I am Anahita and I'm going to present our paper on efficient robot planning for achieving multiple independent partially observable tasks that evolve over time. In a lot of robotics applications, a robot is in charge of multiple tasks. For example, a mobile robot deployed in office buildings should deliver messages, objects, etc. A robot deployed in a restaurant setting should take care of multiple tables and keep switching between them. And a robot deployed in a factory setting should help out multiple factory workers, for example, by providing tools for them. In this work, we will specifically focus on the restaurant setting. However, our approach is applicable on the domains I mentioned earlier. A robot waiter should take care of an ongoing stream of requests, for example, delivering food and taking food orders. The robot should work quickly and respond to customers appropriately to keep everyone satisfied. An action that the robot takes depends on the duration of possible actions, the state of each table, which might not be fully observable, for example, people's satisfaction level, and how the tables evolve over time. In this work, we focus on the class of problems with multiple independent tasks that are partially observable and evolve over time, and we provide efficient and scalable planning algorithms that can address such class of problems. A restaurant with 3 tables is modeled as a restaurant with 3 models. The model associated with each table includes the state of the table, the state of the robot, and the actions that can be executed on that table. We model each table as a partially observable Markov decision process, so a restaurant with n tables has n POM-DP models associated with it. Although we assume that the tables or tasks are independent, the optimal policy of the robot should consider all possible sequences of tasks to achieve them all. So to do planning on such problems, we have to combine the POM-DPs into one large combined model of all POM-DPs. We call this agent POM-DP. The challenge here is that for large number of tasks, solving this agent POM-DP is computationally intractable. For example, for 5 tables, we have 6 seconds of planning time. However, for 7 tables, we have exponentially larger planning time. The contributions of this work are as follows. We formalize the class of problems with multiple independent tasks. We develop optimal, scalable, and real-time planning algorithms that solve the agent POM-DP model more efficiently by decomposing the problem into a series of smaller planning problems and using the solutions to the individual tasks. Before getting into the details of the approach, let's see what we mean by independence. We call a set of n POM-DPs independent if and only if for each 2 of them the following holds. They don't share any state variables, observation variables, and actions, except the no operation action. The transition or observation function for one task does not depend on the states of the other tasks. So for example, in the restaurant setting, this means that table 1 does not get affected by what happens on table 2 or the state of table 2. Given a restaurant setting with 20 tables or tasks, the robot has to build an agent POM-DP model with the 20 tasks and then plan for a fixed horizon. We exploit an observation that given a short horizon of 4 steps, the robot can only attend to a limited number of tasks, for example, 2 tasks. So instead of considering the agent POM-DP with 20 tasks, the robot can consider all possible pairs of tasks and solve series of much smaller planning problems. We go one step further and we prune the set of all pairs to solve the agent POM-DP more efficiently. In summary, we consider subsets of the n tasks with size k, and we leverage the independency between the tasks and the limited task achievement assumption. Our approach is as follows. We consider subsets of the n tasks with size k, for example, for 3 POM-DPs and a 4-step horizon. We consider all pairs. And the efficiency that we are going to get out of this approach is that for 7 tables, we have 21 subsets. However, the model associated with each subset is much smaller than the agent POM-DP model with 7 tables. We prune the subsets by solving the individual POM-DP separately and using their solutions to compute a lower bound on the value of the agent POM-DP and an upper bound on the value of each subset. We compute the lower bound by assuming that the robot can only execute one task in its planning horizon. So the robot can service table 1 or table 3 or table 2. We compute an upper bound on the value of each subset by assuming that after the first action execution, all tasks can be addressed in parallel. And given that we have only one robot, this is going to give us an upper bound. We prune the subsets where the upper bound is less than the lower bound. And then we solve the remaining subsets optimally and select the action with the highest value as the best action. In the paper, we prove that given the assumptions, our approach is optimal. We also evaluate the performance of our approach in a simulated restaurant setting. We run 30 episodes, each for 20 actions. We randomly initialize each episode, and we have 2 to 12 tables in the restaurant model. On the right, you see an example of the restaurant model with 5 tables. Above each table, we have how long the customers have been waiting and what is their current request. Each histogram shows the robot's belief over customer satisfaction. 0 means very unsatisfied and 5 means very satisfied. We compare the performance of our approach, which we call AC POM-DP, against the following approaches. The optimal agent POM-DP approach, the n-samples approach where they select n tuples randomly from all possible tuples and solve them optimally. The hierarchical POM-DP approach, which represents each task as a macro action. So we have n macro actions for all the n tasks. We also compare against the greedy approach. Here we are showing our quantitative results. On the x-axis, we have the number of tables. On the y-axis, we have the difference between the average reward that our approach gets versus all the other approaches. So the 0 constant line is representing our approach. Everything below the line is worse than our approach, and everything above the line is better than our approach. We have plots for different horizons. As you can see, the optimal approaches A and B performs the same. However, the suboptimal approaches perform much worse than our approach. We compare the performance of our approach against the baselines in terms of planning time. On the x-axis, we have the number of tables. On the y-axis, we have the planning time, and we have plots for different horizons. As you can see in the plots, our approach performs much better than the optimal agent POM-DP approach. Although our approach has a higher planning time than the suboptimal approaches, but as we saw in the previous plots, our approach has a much better average reward. We conclude the talk by showing a video of the real robot attending 2-3 tables in a restaurant setting. We show the state of the restaurant on the top left of the video. We added a kitchen area shown as K, and the restaurant has 3 tables. We show the customer's current request and their wait time above each table. We also show the customer satisfaction level. We show the action that the robot is executing on the bottom of the video. You can see that as the robot is servicing different tables, their satisfaction level increases. So here, the robot went to table 2. It gave them the menu and asked them about their order. And you see that table 2's satisfaction level increased. The robot then goes to table 1 and tells them that the food is not ready. And then it goes to table 0. So here the robot is taking an interleaved planning and execution framework where it plans for a fixed short horizon. It executes the action and then replans. Thank you for listening to the talk. I'll take the questions now.